like all to welcome Lars Hupel, who most of you probably know as Lars Hupel. He is a PhD student in München in computer science, and he's the co-founder of TypeLevel, right? TypeLevel,
yes.
Which is responsible for Shapeless and Cats and many other famous libraries. And I had a question from somebody who wanted some special attention. Is maybe Tony Morris in the? I'm kidding, I'm kidding. So, ladies and gentlemen, I would like a warm applause for Lars Hupel.
All right. So we've heard a lot about types now, and my talk is actually entitled "When Types Are Not Enough." Sorry, Edwin, but there's more than that. So I'm a PhD student, as has been already mentioned, and I'm working at a lab for logic and verification. So I'm kind of the mathematical fundamentalist. So we actually care about correctness of programs a lot, and we do proofs and we do all sorts of formal things. And I'm going to give you a quick look into what it's going to entail. So quick show of hands, who of you have been to Paul's workshop, Paul's night, please? Okay, so the good news is that I'm not going to show any kind of low-level things, or I'm not going to rabble on about like what kind of inference steps logic supports. You have seen that at Paul's workshop. I'm going to give you a kind of a high-level description. The downside is that there will be some magic, and you just have to accept that magic. Okay, but let's start. Right, so what is software development? So of course, as you know, there are quite a lot of software methodologies out there, how to develop software. And in Scala, I think if you program in Scala, there's pretty much universal agreement that types and tests together should be used for correctness of programs, to ensure the correctness. Now, the big question is, what actually is correctness of programs? And we've heard a lot about these things at this conference, reasoning about programs, ensuring correctness, and what is it actually? And who actually defines what a correct program is? And I have an example for you. And this should be easy, right? As I'm giving you the task, implement a function which sorts a list of numbers. Easy enough? So who sees a problem with that task?
There's no ordering defined.
Yeah, so the first question is actually, what are numbers? Right? So what kind of numbers are we talking about? Are we talking about real numbers, natural numbers, surreal numbers? And what is sorting actually, you know? Like, how about duplicates? How about ordering? Like, do we want it to be stable? Something like that, right? So this task is extremely underspecified. We don't actually know what to do. So whenever someone claims, I have finished that task, you know this person's lying, because this person couldn't even have known what to do. Right, so this is where specifications come into play. And what are specifications? So in an ideal world, you get from a customer or from the product team, you get like a book or whatever, or document, a formal document, and you can just have a look at it and, you know, study the requirements. It's all written out, it's all very clear, and then you can go on and, you know, you have precise definitions of everything, you can start programming. But the reality is, sadly, that those specifications often don't make sense or might not even exist at all. And that is a big problem in software engineering, but I'm guessing I don't need to tell you that. And if I were to ask you how many customers you have had who gave you a detailed, non-contradictory specification, I'm assuming nobody would raise their hand. So for this talk, however, I'm going to make an assumption, and I'm going to justify this assumption later on when I'm done. And these assumptions are, there's a clear specification, if only for just a subsystem. So for example, if we have given this task of implementing a sort function, I'm going to assume now that we have at least a specification of what sort function is supposed to mean, even if the broader context of the sort function is not yet known. And of course, also, I'm going to assume the specification makes sense, that it doesn't contradict itself, that it's written clearly, and you know, all that stuff. So we have the specification now, and now the question is how to implement this. and how to check that the implementation actually obeys the specification. And we have three main tools for that. So the first tool, the most primitive one of those, is tests. And what tests say is essentially, in these cases I have specified the output is correct. So we give some examples, and then we hardcode essentially the result, and we check if our function computes the correct result. Of course, there are some more sophisticated tools like Scala check or quick check and things like that, which will not try just one case, but maybe 100 cases, but essentially it's the same thing. And the most important point is that tests cannot prove the absence of errors. They just prove the absence of errors for some cases I have thought about. The next level is types. So types essentially tell you that for all inputs, the output is well formed. So if you have a function which sorts a list, or which claims to sort a list, which is maybe called sort, and it takes a list of A and returns a list of A, you know for sure that there's not going to be an option out of that function, or that it won't accept, that you know that it won't accept, I don't know, a string or something like that. You know exactly that the input is going to be a list and the output is going to be a list. But that's about it. That's all you can read from the signature. It's already something, but it's not quite all we want. And the third level, the most advanced level, is the proof level. And this is actually saying for all inputs, the output is correct. So we give actually a definition, we have to give a definition what it means for input to be correct. And then we have to give some evidence, we have to give a proof why that is the case. And the feature here is, or the good thing here is that when you have a proof, it's actually, you know, you have it actually proven for all inputs. So there can be, beyond any reasonable doubt, essentially, your function is going to be correct.
So are you assuming that there are no exceptions?
Yes. Yes, but I'm going to talk about this. Anyway, so Clippy, we haven't seen this guy for a while. It thinks like we were going to prove something. And of course, right now we don't have any idea, so we'll gladly accept some help from Clippy. Anyway, so you have seen in Edwin's talk a little bit about types, and I think it might actually make sense to recall what types actually are. So this is a definition of Benjamin Pierce, which I think is the canonical definition. There are other definitions of types, but this is the one I'm going to stick with. And Benjamin Pierce says that types are basically syntactic. That's the most important point, and they classify phrases, so expressions of your program, according to values they compute. And this is already quite something. And there's a theorem called Kurihara Isomorphism, and this isomorphism tells us that types are propositions and values are proofs. So by the very nature of writing down a type and giving an implementation for this type, you're already kind of performing some proofs. In a dependently typed language like Idris, you actually have a unification between values and types. And this makes this Kurihara, so this actually makes a lot of sense, because you can actually encode quite a lot of things in your types. And just by writing values, you can already write quite some comprehensive proofs. And let's say you have some specific data types, and you can in this data type you can actually encode some invariants. You can do that in dependently typed language. And by the very nature of writing down a program which satisfies this type, you have already proven correctness. So what you've also seen in Edwin's talk is essentially when you write down an implementation of the store protocol, just by writing it down, you have already proven correctness. So there's essentially, I'm arguing, an intrinsic connection between those two things. So there's a limitation though. Let's have a look at Haskell. I chose Haskell just because the syntax for data types is rather short, and I don't have that much space on my slides. So apologies for that. Anyway, so I'm presuming that all of you are familiar with red-black trees in some way. Not necessarily being able to implement them, I wouldn't without looking them up. Anyway, so red-black trees, basic idea is they're just like regular binary trees, but each node has an additional color attached to them. And essentially there's an invariant saying that, I don't know, specific things have to hold about red and black nodes, something like, I don't know, I'm just making this up. A red node must have 2 black children or something like that. I'm not sure if that's actually true, but something along those lines. So what you can do is you can write a data type, and then you can define a function which checks that the invariant is satisfied. This is what you would do in Haskell 98. And this is also what you can do in Idris. This is also what you can do in Scala. This is basically using a very simple type system, and you could imagine writing tests for that, right? So you write an insert function, and you would write a test that after inserting a value into a tree, this isRBT function is still true. But in Haskell and in Idris, you can go even farther than that. So you can actually encode this invariant, this isRBT function, into the type. So essentially what you can say is I have separate constructors for red nodes and for black nodes. And I also put the depth of this current, the current node in the type, so essentially here the depth. And then you can say, okay, my leaves are always black and they have depth 0, and a red node must have 2 black nodes, black children, and something like that. So you can actually do that. So there's a problem though. If you want to implement, for example, the insert function, you will notice that while constructing the tree, you will violate this invariant. And then you have to balance the tree again. So essentially, you figure out where to insert this value, you insert it, and then you have to perform another operation to reconstruct the invariance. So actually, you can't write down this insert function, because the type checker will complain at you because the invariant is violated. So what you have to do is you have to figure out what this violated constraint is, so where exactly it's violated, and you would need to write down a different type, something like tree2 or tree violated, which would capture this violated constraint, and then you have a balance function which transforms a tree2 into a tree1, or original tree essentially. So you have to create another data type essentially. And this is a different approach for doing things, but I'm arguing that this is actually much simpler if you have a system which will allow you to prove that this is actually true. So in Haskell you could just forget for checking that, but there are systems where you can actually check that. And I've prepared a slide here with an overview of some proof systems, and I'm hoping it's not too infuriating. Edwin, please do not read this. So who of you knows at least one of the logos here? 2? 3? All of them? Okay, so this is Isabel. This is the system which is being developed in our lab in Munich. This is Coq. This is PolyML. It's an implementation of the ML language. I just picked the concrete implementation because I couldn't find any logo for ML. And this is Idris. And what I want to tell you with this diagram is basically it has 2 axes. And the horizontal axis says how expressive the type system is. So on the left side you have simple types, like in Haskell 98 or in ML, right? And on the right hand side you have fully dependent types. And on this axis what I'm saying is if this is a programming language or if it's a proof assistant. So PolyML and Idris are both practical general purpose programming languages, and Isabel and Coq are also programming languages, sort of, but they have been designed to be more of a proof assistant. And Idris should probably be a little bit higher here because Idris also has features which could reasonably say it makes it sort of a proof assistant, but I think Edwin will agree that it's primarily a programming language. Okay, he's nodding. Okay, I think I'm good.
Also, the centering makes Idris slightly higher anyway.
Yes, you're correct. Okay, so now back to this example. This is how you would write it in Idris, and or in Cog, and I'm going to argue that you don't always need that, and I'm going to show you actually this system here, and in this system you do it like that. So in this system you would write it like that, and then you prove that you write down that all the insert operations actually satisfy this predicate. Okay. So even if you don't have all these fancy types, you can still do proofs. And what is nice about this is that it actually enforces a separation of the terms and the propositions. So you can just go ahead and implement this insert function without caring about the invariants for now, and then at a later point in your program, you can prove them correct. So that is the final slide, and now I'm going to switch to live proving mode. And live proving mode is slightly more complicated in live programming mode. So I hope you will forgive me for any slight pauses. Okay, so this is the Isabelle system. And if you're wondering what kind of editor that is JEdit. And I believe Isabelle is probably the only project on Earth which uses JEdit as its IDE. But you're going to have to live with that. The interaction is roughly the same. So you type in, it's roughly the same as what Edwin showed in Vim and Atom. So you type in some text, and then you have this output window where the compiler or the proof checker will yell at you if you do something wrong. And because inserting into a red-black tree would be too long and too complicated for the session, I've chosen to do something simpler. So I'm just going to talk about inserting a value into a sorted list. So that's also something like ordered, and it's a nice example. And we're going to choose insertion sort because that's exactly what you can do with that. You can implement a sorting function by just repeatedly inserting something into a sorted list. Right? So let's just get started. You can actually program functionally in Isabelle, and we're going to implement an insertion sort now. Right. So I don't think I have to actually explain the syntax. It's if you've seen some language, some functional language, it should be quite self-explanatory, and it's somewhat an odd mixture between Haskell and ML. It's probably got historic reasons, but yeah, it's fair enough. So what we don't have is this fancy case splitting. So I can't just say please give me an implementation, perform a case split. I have to do it by hand, but it's not going to take very long. So when we want to insert a value into the empty list, of course there's going to be the singleton list. And now the system's already telling me that there's something, there's a missing pattern, and it will helpfully complete it to undefined, but I can just fill that out. So let's say insert x if we have y hash ys, so the hash is just the cons element, which you would write with colon in other languages. And now we have to perform a case distinction, so we have to check if x is actually currently at the correct position, so if we can insert it here, or if we have to continue traversing the list. So we say if x is less than or equal than y. As you can see, Isabelle loves Unicode, and there are a couple of input methods, so you can just write down what you would do if you were a mathematician. And so let's just insert it at this position, so we say x hash y hash ys, or else if we're not at the correct position yet, we have to continue, so we leave the x where it is and say insert y ys. Alright, so that's fairly simple.
Is that the opposite? You're inserting x? Is else y insert x ys?
Say that again?
I think it's else y insert x ys. No?
I don't think so. I think that is actually correct. No, you're right. Yes, of course. So it should be y. Yes, thank you. Okay, so now we can actually have a look at what happens here. So we can, there's a command called value, which will allow us to evaluate function calls. So let's say we want to insert the value 2, which is of type which is a natural number, into the list 1, 3, 4. And this looks correct. Okay, let's pick integers because they pretty print nicely. Okay. So as in Haskell, numbers in Isabelle are polymorphic, and it's sometimes a pain because we have about, I would say, 40 or 50 type classes related to numerics. It's sometimes not really easy to figure out which combination you want. So, okay. Now we need to figure out the correctness, and I've already told you that we need to for that we need to define what correctness actually means. So what does it mean for a list to be sorted? And to do that, we define a so-called inductive predicate. So we define essentially it's sort of like a function where you say this is a list, please check for us if it's sorted. And I'm going to copy paste it because it's a little bit of typing, but it should not be too difficult to understand, I guess. So this is what it looks like. So we have three cases. We say that the empty list is sorted, kind of obvious. And also the single case. So if we have the singleton list consisting of just one element, it's also sorted, kind of obvious too. And now the cons case is a little bit more interesting. So we say that a list of containing at least 2 elements, so x1, x2, and the rest list essentially, is sorted if we can prove that x1 is less or equal than x2, and if x2 and x's is sorted again. Does it make sense? Yes? No? Quick show of hands? Make sense? Okay. So you can read this arrow as kind of I should probably say that. So this arrow here in the function definition here, this one is a function arrow, and this one is a logical implication arrow. So you can read this as from left to right. So if you can prove the first thing, if you can prove the second thing, then we have proven the last thing. Okay. We can also tell the system that we want this function, this inductive predicate to be computable. That's kind of an internal detail. Sorted. Just ignore that. Anyway, now we can write value, and we can ask, is the following list sorted? 1, 2, 3. And where's the buffer? Okay, so that's true. Right, so this is sorted. And if you would manipulate it in some way for it's not sorted. Okay, so now we need to prove that this one, this function is actually correct, so if it satisfies this invariant. And we can do that. So in Isabelle, what we do is we write down a lemma, and this lemma is actually quite easy. It's kind of obvious if you think about it. So we say if we assume that we are getting a sorted list, so if we assume that we have something which is already sorted, then we want to prove that when we insert another element into this, it's still sorted. Right? So this is what an invariant is all about. You get something which satisfies something, and after you've done something to that, it still holds. Okay, and of course now we need to do something about this, because Isabelle is just not going to accept it by itself. In fact, you can see the system has now switched into a specific proving mode, and it will tell you there's one goal. There's one goal you have to prove. It's about that the insert function is sorted. Alright, so the way we prove that is by induction. And induction you might remember from undergrad mathematics, physics, or computer science, anything like that. It's essentially a proof method where you boil down to specific cases. So you essentially perform a case distinction, and if you've been programming, you've probably heard about the term divide and conquer. It's kind of like that. So we need to use our assumptions. So we say using assumptions, and then we say prove induction, and then it will decompose this goal. Right, so we have now 3 subgoals for each of the cases. So if we insert something into the empty list, we want to know whether it's sorted. If we insert something in the singleton list, we want to know if it's sorted. And if we insert something into larger list, we also want to know if it's sorted. Now, let's just do the first case, and the remaining cases, they're a little bit more technical, so I'm going to skip over them. I just want to give you an idea how that works in general. So we can say case empty, and now the goals is switching again. So we say we want to show that sorted insert. So we say if you insert x into the empty list, it should be sorted. And Isabelle comes with a thing called tactics. So you can apply kind of functions on the subgoal, and it will try to simplify the subgoal, or sometimes even solve it completely. So one of the most famous tactics is the so-called simplifier, and it will just try to unfold some definitions. So you can say apply simp, and what it has done is you can see the updated subgoal, so it has evaluated insert x empty list and given you the singleton list. And now we can say, we know that singleton lists are always sorted, so we can say apply rule sorted.single, and no subgoals. So this first case is done, so we can say done, and we could go to the next subgoal. And there's another thing I would like to show you, namely that you can simplify proofs after you've written them. And there are more tactics which support quite some things. So the simp tactic actually supports arguments. So you can say simp add, say give this rule, and it will also do that. And there's also another tool, I can show you that. It's called Sledgehammer. Let me just get it for you. So this is Sledgehammer, and Sledgehammer tries to call different provers, so different external programs, kind of like 4 different ones, as you may or may not see there in this line, and you can just invoke it, and it might be able to figure this proof out for us as well. Yes, so Sledgehammer also found this proof. So if you're in a situation where you have no idea what's going on, no idea how to prove that, you can just say, Sledgehammer, please try to figure it out for me. Anyway, so this is essentially what the proof looks like in Isabelle. And we could do even more here. We could do all the remaining cases, but I'm not going to bore you with that. So there's another. So if you ever run into a situation where you don't want to prove it right now, there's a trick. You can say case single, and now you can say show case, and you can apologize, and the system will just accept this proof. And we can do that for the other case as well. You can say case cons, and we say, okay, please, I have no idea. So it will just accept that. And of course, it will kind of tell you that you're a bad person by highlighting in red, but it will still accept that here in this IDE. If you try to run it on the command line, it will yell at you. So no worries about invalid proofs or something like this. There's always some way the system will yell at you. It will find ways. Okay, so how does that relate to Scala now? Because I've been showing you that, and it's all nice, I suppose. But you know, what can you actually do with that? So now you have this other programming language right here, but you can't really execute it. You would need to start this IDE and, you know, type this value commands and, right. So that's not really useful, but there's actually a thing called the code generator. And the code generator is not the opposite of a dead generator. It actually produces code. So there's a command called export code. And we can say, we can give the functions we want to export. And let's say we want to export both the sorted predicate and the insert function. So we say sorted and insert. And we can now specify the language. And there are 4 languages to choose from. There's Haskell, OCaml, StandardML, and obviously Scala. We can say in Scala. And now let's have a look at the output. And here's your Scala code. So you can actually have the system write that to a file and then just put it into the Scala compiler. And as you can see, there's quite some bit of boilerplate around here. So the system will define its own equality, type classes, and things like that, because it's a mathematical system, and mathematicians have their own idea about equality. And you have product types, tuples, and stuff like that. And then, wait, that's not it. Where is it? Oh, some more stuff going on. Here is it. There's the insert function, and as you can see, it's just like regular Scala code. It's probably not the kind of Scala code you would write by hand, but it usually compiles. So there are some corner cases which have been found like 2 weeks ago, but this was some complicated nested let and case expression, something like that. But I'm using this on a regular basis, and so far I haven't found any of these corner cases by accident. So I think you're quite safe if you dump this to a file, feed it to Scala-Z. The only disadvantage you will have here is that this system tends to use anonymous functions quite a lot. So if you're on a Windows, you might run into this path length problem, but just use Mac or Linux.
Linux also has it. If you encode your home folder, Linux also has it.
Oh yeah, right. Okay, don't do that then. Okay, then you can also export Haskell. So anyway, so what you can do now is essentially you can write your function, you can prove it in a system which has quite a good amount of automation, and then tell it to export this code into a language of your choice, feed it into the compiler, and then you have your own subsystem which you can interface with. You can build pretty APIs on top of that, and you have now subsystem in your code where you know that it's actually proven correct. And people are using that. So there are quite a lot of people out there who do their formalizations in Isabelle, implement their critical systems there, and then export it to like Scala or Haskell, and then build a nicer API on top of that. A colleague of mine, he has verified, or he has implemented IP tables or a subset of IP tables, the Linux firewall, in Isabelle, and then he has written some procedures in Isabelle to simplify firewalls, and then has proven that the firewall behavior is still the same, and then there's a tool exported from Isabelle where you can actually, a system administrator can dump the IP tables firewall in there, it will do some magic, and there's going to be new firewall which is easier and has the same filtering behavior. So I think that's actually quite nice. Right, so how many time do I have left? Still a bit, okay. Any questions so far about the system? Yes?
It's actually for Daniel. I'd like to know when FS2 is going to be extracted from this.
Okay, so the question was when is FS2, so the successor of Scala Stream, is going to be extracted from Isabelle? Daniel, do you want to answer?
I will consider a pull request.
So Daniel is considering the pull request. So there's one thing I have to mention at this point. So the type system of Isabelle is simple, and it's simple for a reason because it does not actually support higher kind of polymorphism. So I think you're going to have problems. Sorry about that. So the strength of the system is not in the type system; it's in the automation, so that you can actually write down things like this, and that you have Sledgehammer available, so that quite a lot of things can be actually solved automatically without you needing to spend a lot of brain cycles on that. And we also get a lot of users from mathematics departments because they kind of like the style that you can write your proofs like in a textbook. So you don't have to write like scripts of instructions, low-level instructions like an assembler to your prover, but you can actually write something like this, which kind of resembles a textbook. Okay, so now I have covered the direction where you write your code in another language and then you extract executable code in Scala from there. But what if you have already Scala code? And what if you want to verify that Scala code after you've written? And fortunately, there's also a tool for that where you can go in the opposite direction. And this tool is called Leon. Where is it? Hello? Does anybody know how to make it bigger in Chrome?
Control plus.
I'm pressing Control plus, but...
Command Shift plus.
Okay, let's try this.
You are at the maximum probably.
It doesn't do anything. Let's reload. Oh, now it... Okay, so this is Scala code. Well, it's not quite Scala code, but it's similar enough. So what Leon essentially is, it's a verification system for Scala. So it feeds, it reads Scala code, and then it looks for specific instructions in there, and then tries to prove the invariance in the program. And it basically, it calls the Scala compiler up to the typing phase, and then it kind of, instead of generating code, it will just analyze the code, so it kind of turns around, and then transforms it into some intermediate representation, and yeah, tries to figure out what to do with that. And I'm not sure how many of you know that the Scala library actually ships with require, assert, and ensuring these functions. How many of you were aware? Right. So, but I guess not many people actually use that. So, and Leon kind of gives them a special meaning. So here's the function, the first function here, the size function. It takes a list and gives you back a big integer. We are using big integers here, not machine integers, because machine integers overflow, and that is terrible for proving because it will actually find counterexamples all the time. So you're actually being forced to use actual natural numbers here, or whole numbers, instead of these machine integers from the devil. So this function is going to compute the size of a list, and this looks easy enough, right? So you do pattern matching and you return 0 if it's empty and 1 plus the rest if it's non-empty. And with this ensuring, I can tell the system I want the result value to be greater or equal than 0. So if I now go ahead and do something wrong here, so for example, let's say I'm producing -1 here instead of 0, the system will figure that out in a second. It will compile it again and verify it, and now it will say there's something wrong here. So I can click on this marker, on this little red exclamation mark, and it will tell me that there's a counterexample. It found a counterexample. So if you give the function the empty list, it will give you back -1, and that's invalid because we wanted something greater or equal than 0. And look at this, there's a repair button. And it found something. Now you can actually click on import now. See what it did for you. So it actually fixed that function for you. How good is that?
Who needs Idris?
Sorry?
Who needs Idris?
Yeah. Who needs Idris? No one. If the computer can actually fix your programs for you. Okay, so I have a little bit of time left, so I can show you this insert function example as well in Scala. So I've already defined this sorted function for you. It looks kind of similar. So you do case analysis again, and check if your list is sorted. And now let's write the insert function. So we say dash insert, and we're going to take an x because functional programmers call things x. And we also need let's just do this big integers here. So we say access list big int, and we want another list of big int back. So we say access match. Right. So if it's empty, we give back cons x nil. So as you can see, it's not quite Scala. So there's not the nil has parentheses right here, and you have instead of colon colon you have cons, but it's fair enough. And if you have cons y ys, say okay. So if x is less or equal than y, we can return cons x cons y ys, or else it's going to be cons y insert and x and y. Is that correct? Something wrong? Can you see the problem? Oh, additional. Okay, so this compiles fine, but we haven't actually given any specification yet. So let's just say we add the specification, and we can do that with the ensuring function. So we say ensuring, and now we take the result, which is a list of big int, and we say this should be sorted. Okay. Okay, so it found the condition, it found the invariant, but it's actually wrong. So we can click here, and it actually found a counterexample. It's quite a big counterexample, but so do you know what the problem was? What?
The input sorted.
Yes. So the input wasn't sorted, so we need to fix that. And I'm not going to click on repair here because I don't actually know if it would be able to repair it. So, but we can just say require is sorted access and fix the parentheses. So this and that. Right. So now it's actually verified it. There's a check mark. So now the system is satisfied. We have a correct insert function. All is well. And we can even go a little bit farther. So the system does not just have an insert function and repair function. It also has a synthesis function. So we can just leave a hold in our program and tell the whole what we want. So we can just take our ensuring here. We can say. Can now go here and remove that. You can say choose And people who have been looking at the difference between classical logic and constructive logic will know this as the peculiar Hilbert's choice operator. And this is not actually executable, but the system will look at this, find, okay, there's a hole in here, so we can click on that. We can now click on search, and it will find something. Click on import. Does anyone see what's wrong here?
I think it is sorted.
It is sorted. The result is sorted, but can you see a problem with the result? So of course we forgot to specify that the elements in the result list should also be the same as we have put into the list. But we could add that, and the system would find that. And I think I'm about on time. So you can give the system a try. It's actually online. It's under leon.epfl.ch. You can give it a try. You can also give Isabel a try. So if you Google for Isabel Prover, you will also find it. Yeah, but I hope you enjoyed this demonstration. And any questions? I should probably also remark that this is a very good example of what happens if your specification is wrong. Because this is a valid implementation of a specification, but not what you want.
How well does Leon do with polymorphism?
So the question was what Leon does with polymorphism. And it does support polymorphism, but in this case, I couldn't actually use it because it does not support implicits or type classes in that sense. So these comparison operators, they are monomorphic, essentially. So you can't, as of now, say, like in Isabel, you have a type T, which has an ordering, and then it would use the comparison operator of the ordering. You can't do that. I think the underlying problem is that it would require subtype polymorphism, and this is not implemented yet, but I don't see any reason why it can't be implemented at some point. But it just isn't done right. Okay, another question?
When you got Isabel to generate Scala code, it looked like it generated your type classes for you. Is there any way to say, sort of don't generate an order type class, use the one in Scala Z order or something like that?
So the question was, when you go to Isabel and ask it to export some code, it will generate all its type classes by its own, and it won't reuse some existing ones. And in fact, there is a way to do that. So you can, there's a command called code printing, and you can tell the system that, there's already a list type in Scala, use that instead. I'm not sure if it extends to type classes. I'm pretty sure it extends to functions and types. The only problem is that if you customize this, the code generator obviously can't check if your mapping is correct. So you have an additional kind of insecurity in your translation. So people do use this code printing though, and it's just, you have to keep in mind that when you generate the code, you have to make sure that your mappings are actually correct.
No further question?
Then thanks.
In that case, thank you very much. Goodbye. We'll take a short half-hour break, and after that I hope to see you all back.